Have you ever just watched a robotic arm move and wondered how it gets that incredible precision? Or, how a car engine turns simple rotation into powerful linear motion? Well, the secret sauce behind a lot of that is a surprisingly simple mechanism, the four-bar linkage. And today, we're going to unpack the brilliant math behind it. We'll use what's called the vector loop closure method to figure out its exact position at any time. This stuff is really the bedrock of so much of modern machine design.
So here's our game plan. First, we're going to tackle the why, as in, why just sketching this stuff out on paper doesn't work anymore. Then we'll translate this physical machine into a really clean vector equation. After that, we dive headfirst into the algebraic puzzle that's at the heart of this whole thing. And the payoff? We're going to see our math turn into a dynamic, moving simulation. It's going to be great. Let's get into it.
All right, first up, sketch versus simulation. Before we start throwing equations around, let's get a handle on why we even need them in the first place. I mean, why go through all this trouble when you could just draw it out, right? Well, let's see why that's not quite enough.
And this slide really gets to the heart of it. Over on the left, you've got the old-school graphical methods. And look, they're great for a quick back-of-the-napkin sketch to get a feel for things. But they're also slow, and worse, they're imprecise. You just can't build a modern robot or a high-performance engine based on guesswork. That's where the analytical approach on the right comes in. It gives us exact, totally bulletproof equations for any possible position. This is the language computers get, and it's what makes all the powerful simulations we rely on in modern engineering possible. This is exactly why we need the math.
Okay, moving on to section 2, the vector loop equation. This is where we start translating the physical hardware, the actual metal and bolts, into the pure, universal language of mathematics.
So the way we start is by looking at this mechanism in a totally new light. Imagine each link isn't just a bar, but it's a vector. It has a length and it has an angle. Now, since they're all hooked together in a loop, it means if you start at one point and you follow the vectors all the way around, you have to end up right back where you started. It's that simple. And that little geometric fact gives us our key, the vector loop closure equation. All it's saying is that going over the top, through the crank and the coupler, is the exact same as going along the bottom, through the ground link and the rocker. And believe it or not, this one simple equation governs the entire motion of this machine.
And here's where things get really interesting. That one vector equation, it's actually hiding two separate equations inside of it. You've got one for the horizontal, or x direction, and another for the vertical, y direction. Now, we know all our link lengths, right? And we know the input angle, theta 2. So the whole game now is to figure out the two unknowns, the coupler's angle, theta 3, and the rocker's angle, theta 4. But here's the catch. These equations are all tangled up. You can't solve for one without knowing the other. It's a classic chicken and egg problem, and cracking it is going to take a pretty clever strategy.
And that brings us to the main event, solving the algebraic puzzle. This is the core of it all. Let's walk through the derivation step by step. Okay, so our first strategic move is to solve for theta 4. But to do that, we have got to get that annoying theta 3 out of the picture. And the strategy here is it's beautiful. First, we shuffle our two equations around to get all the theta 3 terms by themselves on one side. Now, get ready for the magic trick. We're going to square both sides of both of these equations. And then, we're just going to add them together. Why would we do that? Because of that famous trig identity you probably remember, cosine squared plus sine squared equals 1. When we do this, the left side of our equation simplifies like a dream, and bam! Just like that, theta 3 completely vanishes. It's a brilliant piece of algebraic jujitsu.
So with theta 3 gone, we're left with this beast of an equation that only has our target, theta 4, in it. And at first glance, it looks like an absolute mess. But watch what happens when we expand all the terms and start tidying up. We can group together all the cosine terms, all the sine terms, and all the constant terms. And what's incredible is, when you do that, all that mess just melts away into this super clean, standard form, a times cosine theta 4 plus b times sine theta 4 plus c equals 0. And the best part, for any input angle we choose, a, b, and c are just numbers we can calculate. Easy.
So how in the world do we solve this? We've still got sines and cosines all mixed up. Well, we pull out a really clever tool from the mathematician's toolbox called the tangent half-angle substitution. It's basically a sneaky way to express both sine and cosine using just one new variable, t. And when we plug these into our equation, all the trig just disappears. The problem magically transforms into a standard quadratic equation. This is something we've all known how to solve since high school. We took a really tough problem and turned it into something familiar.
And now we can just use the good old quadratic formula to solve for our variable t. Now, see that plus or minus sign in there? That is a huge clue. It's telling us that we're actually going to get two possible solutions. Hang on to that thought. It's going to be really important in a minute. And by the way, if that number under the square root ever turns out to be negative, it literally means the links can't connect at that input angle. So, with our value for t, or values I should say, we can find theta 4. Okay, so now that we know theta 4, we can finally go back and hunt down theta 3. But I've got one last pro tip for you. We use a special function called ATN2. Now, unlike a regular arctangent, it looks at the signs of both the top and bottom parts of the fraction, and that lets it figure out the exact quadrant the angle should be in. No guesswork, no ambiguity. And just like that, we've done it. Our analytical solution is complete.
So what about that plus or minus sigma from the math? What was that all about? Well, it's not just some weird thing the math spit out. It represents the two totally different, physically real ways a 4-bar linkage can be put together. Any real mechanism has to exist in one of these assembly modes. Sigma equals +1 usually gives you what we call an elbow up configuration, while sigma equals -1 gives you the elbow down mode. They're basically mirror images of each other, both perfectly valid.
Okay, let's make this real. Let's plug in some numbers and see it work. Using the dimensions from our very first slide and an input angle of 0 degrees, we can just walk through the calculation. First, we find our coefficients, a, b, and c. Then we solve for t and get our output angle for theta 4, which comes out to about 53.6 degrees. And finally, we plug that result back in to find theta 3, which is about 66.9 degrees. See? The math checks out perfectly.
All right, this is the moment we've been waiting for. This is the really satisfying part. Let's see how we can turn all of this theory, all of this math, into actual living motion.
And this right here is where all that hard work really pays off. The true power of an analytical solution is seeing how cleanly it just translates right into code. On the left, you've got the formulas we just derived, and on the right, a simple Python function that puts them to work. You can see it. It calculates a, b, and c, it solves the quadratic for t, and it uses that ATAN2 function to get the final angles. Think about that. This little function can now solve the linkages position for any angle you throw at it, instantly.
So what happens when we tell our code to calculate the position not just once, but for every single degree in a full 360-degree rotation? Well, you get this. We bring the kinematics to life. Here's our first solution, assembly mode 1, with that classic elbow up motion we talked about. All of this generated from just a few simple lines of code. And what about that second solution our math promised us? You know, the one from the minus sign? Well, all we have to do is flip one single variable in our code, from a +1 to a -1, and run it again. And there it is. The exact same set of equations gives us a completely different but equally valid motion, the elbow down mode. I mean, this is the beauty of it all. The mathematics perfectly captures the dual physical nature of the machine.
All right, let's bring it all home. Let's wrap this up by summarizing what we've accomplished and, more importantly, looking at where this all leads.
So let's recap. We have successfully derived a complete closed-form solution for the position of a 4-bar linkage. We now have the exact mathematical tool we need for any kind of computer simulation. But you know, knowing where the linkage is, that's really just the beginning. The next big question is, what's next? Well, by differentiating these very same equations, we can start to unlock the secrets of its velocity and its acceleration, and that opens the door to understanding the forces at play inside the machine, which is the real key to designing stronger, faster, and more efficient machines. We've laid the foundation, and from here, our understanding of how machines really move can only get deeper.